So the talk is called Breaking the Logarithmic Barrier in Roth Theorem and Arithmetic Progressions. This talk and the paper and everything I say today is all joint work with Olof Sisask at Stockholm University. And the paper containing the proof and the result that I'm going to talk about today is already in the archive. It appeared there on Wednesday morning. So that's, and the paper is of the same title, if you'd like to go and investigate further. So the plan for the talk is roughly as follows. So I'm going to start the first, as Sean said, the talk's going to be a little longer than usual, possibly about an hour and a half, partially because I expect there is probably quite a range of backgrounds in the audience, some of whom might be quite new to the topic of Roth theorem and the type of techniques involved. And I really want to try and give something of use to those people as well as the experts in the audience who sort of are already up to speed on all of the background and the context and really want to know what the new methods introduced are. So the first half of the talk, I'll give a bit of historical background and context and talk about the results and a very high level overview of the sketch of the proof. And then we'll break for a couple of minutes, have a drink of water, I'll possibly answer a couple of questions. And then we'll go into a bit more detail on some of the key steps of the proof after the break. Okay, so we begin with a definition. It's a very classic definition. So that R of n denote the largest possible size of a set A in the interval 1 up to n, which contains no non-trivial three-term arithmetic progressions. So by this, I just mean three numbers of the form x, x plus d, and x plus 2d, and it's non-trivial because I'm insisting that d is not equal to 0. If I just say three-term progressions, generally that includes the trivial ones where d equals 0 as well, but those are easy to count. So this quantity R of n was first considered by Erdos and Turan in 1936, and in a really beautiful short paper, they introduced this quantity and they showed by an ingenious, elegant short argument some non-trivial upper bounds on R of n. So in that paper, they proved that it's the most basically 3/8 of n. And they conjectured in that paper as well that R of n is little o of n. So in particular that any positive density subset of the integers, for example, contains three-term arithmetic progressions. So this qualitative statement, that R of n is little o of n, was proved by Roth in 1953. And in fact, curiously, the first proof of this qualitative method actually gave fairly good quantitative upper bounds as well. So in his original paper, Roth proved the upper bound R of n is less than n over log n. I guess I'll point out now, by the way, this notation less than, if you haven't seen it much before, if you're new to the field, in this context, it's the Vinogradov notation, which means less than or equal to that quantity times some absolute constant. Okay, so we're not going to really keep track of absolute constants in this talk. So this original bound of Roth of n over log n has seen repeated improvements, so which I've summarized in a couple of slides. So the original bound of Roth in 1953 was n over log n. This was improved by Zemerady to sort of a bound in between powers of log and powers of log. I think actually this bound itself, sort of unpublished lecture notes or a conference talk by Zemerady in 86. And then those ideas were pushed further by Heath Brown, who in 87 proved the first polylogarithmic bound. So n over log n to the c for some tiny constant c, but in principle computable. And then Zemerady pushed those ideas a little further and obtained the value of 1/4 for the constant c. And in fact, also in that paper, he discusses how that method somehow has a hard limit of c equals 1/3. So in principle, I don't know if this has actually been done anywhere, but in principle, one could use the sort of methods of Zemerady and Heath Brown to get n over log n to the 1/3. For example, we're using quite classical analytic number theory. And then one of the big breakthroughs in the subject came in 99 when Bourgain proved the bound of basically n over square root log n. And I mean, so this paper introduced a lot of new concepts and ideas to the area. And one of the most significant, which will play a big role in this proof in this talk, is something called Bohr sets. So it was really the introduction of Bohr sets over arithmetic progressions, for example, which allowed for this push past log n to the 1/3 to log n to the 1/2. So this was then improved by Bourgain in 2008 to log n to the 2/3, essentially up to log factors, and then further improved by Sanders to log n to the 3/4, And then finally, Tom Sanders in 2011 basically improved this to n over log n, again, up to the log factors. So in his original paper, it was log n to the 6th. And since the original advance of Sanders, there are now, I guess, 3 new proofs of this n over log n density bound, which vary slightly in the log parameters. So a variant proof I gave in 2014. Last year, myself and Olof Sisask presented another proof using, again, different methods. And in fact, just a couple of months ago, the record was achieved by Thomas Schoen, I think in 2 or 3 months ago, who actually gave a talk in this webinar series, where he achieved basically n times log n to the 3 over log n. And I will come back and say something about the various ideas that went into this later on. That's sort of the rough history of the bounds. And all of the previous results that I've mentioned, so all of the 11 bounds there, they all use essentially the same density increment method, which was introduced by Roth in the 50s. And in particular, they all use they all make some use of Fourier analysis and a density increment approach. In terms of the qualitative result, that R of n is little o of n, so that positive density subsets contain 3-term progressions. In fact, since the original argument of Roth, we now know several quite different methods of achieving this, some of which don't use any Fourier analysis at all. So there are proofs now using ergodic theory, for example, and there are very combinatorial proofs as well that are essentially almost entirely graph theory. But so far, none of these alternative methods have really come close to rivaling what Fourier analysis can accomplish in terms of these quantitative strengths. So for example, there is a proof using essentially something from the Zimmer-Rady regularity lemma in graph theory, but that gives you an upper bound which would be sort of tower type bounds, so certainly far worse than the n over log n original bound of Roth. So and our proof is no different. We also work within this density increment Fourier analytic context. And I guess the other thing to stress is that in somehow the exact forms of these bounds are not particularly important, right? So the fact that this is 2/3 rather than 5/7 or something like that, it's really just each of these successive improvements is the result of a significant, at least one, and sometimes more significant new ideas in how we really use harmonic analysis to try and understand the additive behavior of sets of integers. And fortunately, almost always, a significant new idea also translates into some quantitative progress as well. So the result that I'm going to talk about today, which is joint with Olof Sisask, is a further improvement on this upper bound for R of n. So it's the upper bound that R of n is at most, again, some constant, times n over log n to the 1 plus c. So c is greater than 0, and it's left unspecified. It is in principle effective and computable. We haven't worked out an exact value for c. In theory, one could do this by sitting down with our paper and going through it line by line and keeping track of all the implicit constants. But this would really be a very long, arduous process. And also, you would certainly not get a very good value of C out at the end of it anyway. So a back of the envelope calculation suggests, for example, that we think somewhere in the order of magnitude of 2 to the minus 2 to the 2 to the 1000 is the sort of the size of C that one could achieve using our method, for example. So something basically sort of triply exponentially small. So certainly nowhere near C equals a half or any reasonable constant. But in particular, it is an actual universal absolute constant that is greater than 0. In particular, this means that this upper bound is little o of n over log n. And so as a corollary, we actually obtained the first non-trivial case of a conjecture of Erdos on arithmetic progressions. So Erdos conjectured that if you have a set of integers of which the sum of reciprocals diverges, then A contains arbitrarily long arithmetic progressions. And in particular, this sort of roughly corresponds to achieving a density barrier of n going past n over log n. So one can show, for example, that if the density of A is larger than 1 over log n to the 1 plus c, then the sum of reciprocals must converge. So in particular, if a set contains no, must diverge, sorry. So if a set of integers contains no three-term progression, then the sum of reciprocals must converge. Erdos was actually motivated partially in making this conjecture, I think, by thinking about the prime numbers for whom the sets of reciprocals diverge, and for whom it was also conjectured that they contain arbitrarily long arithmetic progressions. It's a fascinating conjecture of Erdos because it shows that he thought this was true not because of any sort of special arithmetic properties of the primes, but merely just because there are a lot of primes. So obviously by the prime number theorem, or weaker estimates, we know there are roughly n over log n primes in 1 up to n, which sort of is roughly about the threshold that this logarithmic density barrier achieves. And of course, famously since then, actually we know this is true about the primes not by establishing this conjecture of Erdos. So Green and Tao have proved that the primes themselves do contain arbitrarily long arithmetic progressions, and indeed dense subsets of the primes do contain arbitrarily long arithmetic progressions. But they do it not by establishing this conjecture, but by using some quite special properties of the primes. But as a corollary of this, I guess, of our theorem on the previous slide, we also see that any subset of the primes of relative positive density contains a three-term arithmetic progression. So again, actually that special case was known before the Green-Tao theorem. That's a result of Green. And as a corollary, we established this just because of the density of the primes rather than any particular arithmetic information about them. So let's go back to point out the form of the result. This sort of type of upper bound of n over log n to the 1 plus c might look a little strange to you if you're sort of a relative newcomer to the area. Indeed, sort of 1 plus 2 to the minus 2 to the 2 to the 1000 is certainly not at all a natural exponent to c, and it seems like a very sort of strange result to prove. But the form of this result won't come as a surprise to many in the area, because it is an analogous sort of result to a breakthrough result by Bateman and Katz about 10 years ago. So they proved a similar upper bound for a related quantity. So if I replace the interval 1 up to n by the finite abelian group f3 to the n, say, then I can still ask the same question. So I can ask, what is the largest size of a subset of f3 to the n which contains no non-trivial three-term arithmetic progressions? So this is often known as the CAP-set problem. And for a long time, I guess since the mid-90s, there was a Fourier analytic argument of Mechelin, which in some sense was a f3 to the n version of what Roth did in the 50s, that established an upper bound of 3 to the n divided by n. And there the matter stood for a long time until this breakthrough result of Bateman and Katz, where they proved an upper bound, again, still a little bit below this logarithmic barrier of 3 to the n divided by n to the 1 plus c. So the use of f3 to the n as kind of this model setting for the integers is well known. So the idea has been around for a long time that, in some sense, for a lot of especially problems in additive combinatorics, we expect the integers to behave in many sense like an arbitrary finite abelian group. So in particular, if we pick a finite abelian group that's somehow easier to work with, for example, a vector space over a finite field, then we can sort of try and understand the problem there and hope that any sort of advance or methods there will generalize to the integers. And in particular, when this result of Bateman and Katz came out, especially because it did use the Fourier analytic techniques, this density increment framework that had been very successful in the integers so far, I think it was definitely raised the hope that by sort of adapting their methods, a similar kind of bound could be achieved for the integers as well. And I guess you can view this result of myself and Olof as fulfilling this, this hope. And so certainly one thing to stress is that our proof definitely does really heavily use a lot of the ideas of Bateman and Katz translated to the integers. So it's certainly not a straightforward translation. There are a lot of difficulties in working out exactly how to get these methods to apply to the integers rather than f3 to the n. And there are several new ideas as well that weren't present in the capset problem case that we've had to introduce to prove this result in the integers. But certainly our paper and our result would not have been possible without this previous breakthrough of Bateman and Katz, and which is full of really beautiful ideas that were very helpful. So of course, having said that the f3 to the n, the capset problem, is a great model case for the integers, it was believed for a long time. The story has an interesting twist, because between the Bateman and Katz result and this present result I'm talking about today in the integers, actually a completely different result, a completely different method was invented for dealing with polynomial arithmetic progressions in f3 to the n. This time coming from the polynomial method, so a very much more algebraic, rigid method. So in particular in 2016, Kreutler and Pach introduced a new polynomial method, which Ellenberg and Hiswit used to prove an upper bound for this quantity r of f3 to the n of something like 2.756 to the n. So just for comparison, this is compared to the Bateman-Katz bound of 3 to the n divided by something a little bit better than n to the 1 plus small constant c. So in particular, this polynomial method sort of dramatically let pass the logarithmic barrier, and in fact proved a density upper bound which was exponentially good. Unfortunately, there really doesn't seem to be any way to adapt this polynomial method to the integers. It seems to be quite special to the fact we're working in groups of, say, for example, small characteristic and very large dimension, which is somehow the opposite end of the spectrum to the integers or cyclic groups of z mod nz, which have basically dimension 1 and very large characteristic. Unlike the Fourier analytic techniques used by Roth and others, and in particular heavily used by Bateman and Katz, which in theory are much more easily generalized to any finite abelian group. So finally, in the background section, I just want to talk about where the truth likely lies, because again, it's certainly very unlikely to be true that the correct answer for this problem is n divided by log n to the 1 plus some tiny constant c. Right? I mean, there is no fair universe in which that is the correct truth for this problem. The correct lower bound, indeed, is much, much smaller than this. So it's originally due, a bound of the shape is due to Behrend. There have been slight refinements in recent years by Elkin and Green and Wolf. But essentially, the lower bound is still of the same strength as Behrend's bound from the 40s, which is r of n is at least n times e to the minus square root log n, with some constants thrown in. So in particular, that's sort of smaller than any power of log n. And we believe that the lower bound is closer to the truth. Right? So for example, we don't believe that the correct answer is n over log n squared or n over log n cubed or anything like that. And we conjecture that in fact there exists some constant c greater than 0, still an absolute constant which bears no relation to the other constant c on this slide, such that r of n is at most exponential in minus log n to the c times, that should be capital N. So of course, the Behrend lower bound shows that we can't hope to do better than c equals a half there. And indeed, one might give the stronger conjecture that c equals a half is actually possible. We're not conjecturing that. I think Olof and I agree that we wouldn't be surprised if it turned out that c equals a half is the correct answer, but also we wouldn't be particularly surprised if it turns out that the truth is something more like c equals 1/3 or possibly even c equals 1/4 or something. So I guess we're hedging our bets and just saying that we believe it's certainly better than any power of log, and is of this form. This conjecture has something of this form that's been around in sort of folklore in the community for a long time. Okay, so I've stated the results and given a bit of the historical background. I'm now going to give a very high-level overview of the sketch of the proof. I guess is now a good time to just pause in case there's any quick question or two about anything in the previous section. I'm not seeing the chat window, so I don't know if there's been anything coming in.
There's nothing in the chat at the moment.
Okay, great. I'll press on them. Yeah, so I'm going to give a very high level overview of the sketch of the proof. I expect there's probably sort of roughly 3 classes of people in the audience today. There's people who are sort of relative newcomers to the whole area of Roth's theorem, this density increment approach. There's people who are possibly very familiar with the more classical approach of Roth and then Morgan, Sanders, but aren't really familiar with the ideas of Bateman and Katz. And then there's probably a few experts as well who are also very familiar with the ideas of Bateman and Katz and sort of just want to see about what the key new twists we've done to their method to get it to work in the integers are. So hopefully I'll say something of use to all 3 types of audience member, but obviously of necessity, all 3 types will probably leave feeling slightly unsatisfied, but in the interest of keeping the talk to just an hour and a half, I'll have to omit many details. Okay. So in terms of what the proof is, in terms of what the proof involves, I first of all want to give a bit of a preamble in terms of the type of methods that it uses. So in general, most of the previous improvements have come from a new idea on the frequency side. So that is the idea of sort of translating the problem about 3-term progressions to a problem about Fourier coefficients goes all the way back to the original approach of Roth. And then a lot of these quantitative improvements have come from a new idea or several new ideas about how to really work with these sets of large Fourier coefficients and try to understand the structure in them. And I think one of the reasons that Sanders managed to sort of prove this bound of basically n over log n was that he sort of combined some of these very powerful Fourier techniques with some recent very powerful techniques on the physical side. So sort of that is purely combinatorial methods that are more probabilistic in nature and don't use Fourier analysis. And it was sort of by combining these both that he used n over log n. In my 2014 paper, I gave an alternative proof that sort of abandoned these new Fourier, these new physical methods of almost periodicity, and instead gave, I guess, in a way, more traditional proof using just properties of the frequency set of the set of large Fourier coefficients. And then in last year's paper with Olof Sisask, we gave a third alternative approach that this time used hardly any Fourier analysis at all, and instead really used almost entirely this new almost periodicity physical method. And in this proof, we once again return to, just as with the Sanders original proof of n over log n, sort of using both techniques in quite a vital way. And it's my belief, at least, that I think this is really necessary. I don't think that to really push past this density barrier of 1 over log n, I don't believe you can do that using solely Fourier analytic arguments or solely combinatorial arguments. I think it is really the fact that we are making use of both directions of attack simultaneously, I guess, that allow us to push a little bit past this 1 over log n barrier. Okay. And although a lot of the rest of the talk is going to be talking about these sort of sets of large Fourier coefficients and frequency methods, there are several points where we, in the paper, where we really do make heavy use of this almost periodicity technique. And I will try and point that out in the talk where that happens, although I won't be able to go into much of the details about how that works. Okay, so how does one prove something like Roth's theorem? So we're going to fix some finite abelian group G of odd order, and you can think of this as being, say, f3 to the n or z mod nz for odd n. And so capital N will in general denote the size of the group. Our methods are very robust. In particular, our final result does actually apply to any finite abelian group of odd order. When I talk about the density of a set, I'll mean its normalized size, so denoted by alpha, and that's just the size of A divided by n. And as previously mentioned, we're going to use the density increment and Fourier analytic approach initiated by Roth. So in general, with analytic, in common with many analytic methods, when we our final result is sort of a combinatorial statement, right? It's about if I have a set A that has a certain common square property, there's an upper bound on its size. But in fact, our analytic techniques mean that we will prove this by proving a lower bound on the count of solutions to an equation. So in particular, if I let T of A be the normalized count of 3-term arithmetic progressions, so that's just the number of triples of the form x, x plus d, and x plus 2d inside A, are normalized divided by n squared. So in particular, this will be a quantity between 0 and 1. Then actually our method will give a lower bound for T of A in terms of the density of A, and that's a lower bound that works whatever the density of A is, whatever A is, as long as it has a fixed density alpha. It's easy to deduce from that an upper bound on the side of sets without 3-term progressions, because of course, if a set has no non-trivial 3-term progressions, then we know exactly what T of A is. T of A is just counting the trivial progressions, of which there are just exactly the size of A many. So in other words, T of A will be exactly alpha divided by n in such a case. So alpha divided by n, I can then combine that with my lower bound for T of A, and hence get an upper bound for alpha. Okay. So how do we hope to get a lower bound for T of A? So the idea of the density increment strategy is to exploit something which is often called the randomness versus structure dichotomy. And this goes something like the following. Either T of A is large, and in particular, we say T of A is, say, roughly, let's say, a half times alpha cubed. And so A has many 3-term progressions. Why alpha cubed? Because this is basically what the number of normalized count of 3-term progressions we expect in a random set of density alpha. Okay, so that's it's fairly straightforward calculation to do. If you have if you take a random subset, say of 1 up to n, or a general finite abelian group of size n of density alpha, then as long as alpha is not very, very small, the number of 3-term progressions is going to be very close to alpha cubed times n squared. Okay, so either we have many progressions, which means A looks like a random set, or again, in this sort of randomness versus structure dichotomy, if A is not behaving like a random set, it should behave like a structured set. And in this context, that means that we expect A to have a strong density increment, which means that there exists some subgroup, say G primed in G, such that the relative density inside G primed, so if I look at A intersect G primed and look at the size of that compared to the ambient group G primed, then that's bigger than alpha, right? Which is quite atypical for a random set, for example. If I take a random set and I intersect it with a reasonably sized subgroup, I expect to still get density alpha. Okay, so this is some divergence from the random case, and it's some small amount of structure. And then I can iterate this argument, because now again I have some subset of a group. So this time it's A intersect G prime instead of A and G prime instead of G, but I still have a subset of a group with a given density that I understand fairly well. So I can just start again at step 1. So either T of A primed is large, for example, or I can get a density increment of A primed, and then density increment of A double primed, and so on and so on and so on, while step 1 continues to fail. Now, the point is that this can't continue forever, right? Because the density can't exceed 1, so I can't keep increasing the density, I can't keep being in step 2. So at some point we have to end in step 1, and there we have a lower bound for some T of A primed, where A primed is some subset of A, and in particular, trivially, that gives us a lower bound for T of A itself, right? Now, it's not obvious that this will give you sort of anything at all without saying something more about case 2, in particular, how much of a density increase have we gotten, and what is G primed, right? So for example, trivially, if I've been a bit silly and I've accidentally chosen G prime to just be the trivial subgroup of just the identity, then I might have achieved the density increment of going straight up to 1, for example, from alpha, but that's not particularly useful at all. So I need to make sure 2 things. Firstly, that the size of G primed isn't too much different from the size of G, so I haven't sort of lost too much in step 2. And also that the density increment I've achieved is actually reasonably large. Okay, so in particular, that means that I can't run the iteration for too many stages. Okay. And the number of times I run the iteration is quite tightly controlled by how much the density of A primed has increased at each stage. Okay. So in terms of what the final quantitative strength of the result one gets, that's a very direct function of these two parameters. So how much does the density increase at each stage, and how much does the size of the subgroup decrease at each stage? To keep this talk from being too technical and sort of chasing around parameters, again, I'm not really going to talk about the quantitative strength of the kind of increments that we achieve. You can consult the paper for that. So in the paper, I should mention, by the way, we give a fairly quantitative, careful sketch of the whole proof, so you can sort of consult there to see how the various parameters change and how they give you the final result. But for the purpose of this talk, I'll keep things qualitative and try and focus on instead on the main new ideas that go in, and then I guess you can take it on faith that they do indeed produce the kind of quantitative gains that we require. Okay, so there are a couple of remarks, I guess, to make about this sort of density increment scheme. The first is, what do I mean by subgroup? Do I actually mean subgroup? This works very well as written, for example, in F3 to the n, where there's loads of subgroups, right? If I'm working in vector space over a finite field, then I have plenty of substructures, very sort of rigid algebraic substructures to pass to. But in general, of course, there might not be any non-trivial subgroups around that I can actually pass to. So certainly to make this approach work for more general finite abelian groups like the cyclic group Z mod nz, I need to have a bit more flexibility in my argument, and indeed must use some notion of approximate subgroup rather than asking for actual subgroups. So Roth's original approach, for example, I mean, it certainly wasn't phrased in these terms. It was phrased more in the language of the circle method and using the whole group of the integers rather than truncating it to a cyclic group, for example. But in hindsight, one can phrase Roth's original argument in this way. And in that approach, the subgroup type objects are arithmetic progressions, right, which enjoy a lot of, which are very structured sets. They have small doubling constant, for instance, and they enjoy a lot of the properties that we want. And one of the key advances, as I mentioned before, in Bourgain's 99 paper, is that Bourgain replaced using arithmetic progressions in this kind of iteration with using Bohr sets instead. So yeah, I won't give a technical definition of what Bohr sets are. They are approximate level sets of characters, if that combination of words means anything to you. If not, you can think of them as being basically multi-dimensional arithmetic progressions. So instead of, for example, instead of just using one parameter, which is arithmetic progression, which is a sort of a projection of a one-dimensional interval into my group, I can instead consider a projection of, say, a d-dimensional cube into my group instead. And that's roughly what Bohr sets correspond to. And it turns out, I mean, this extra freedom of allowing the dimension to grow, for example, as long as the step size and the length of the progression really offers a huge amount of extra freedom, which means this iterative argument can be run much more efficiently. And that's sort of really the reason that Bourgain managed to get the quantitative improvement that he did. Unfortunately, although these Bohr sets are definitely the right objects, they're really beautiful objects to work with. There's a lot of fascinating theory about them, and they're used all over the place as well, not just in studying Roth's theorem, but all over additive combinatorics and beyond. They are definitely not actually subgroups, right? And in some sense, they are approximately subgroups, and in some senses, they are definitely very much not like subgroups at all. So for example, most notably, their doubling constant isn't necessarily small. So with an arithmetic progression, right, the doubling constant is basically 2. But if I'm looking at an arithmetic progression instead of dimension d, the doubling constant is instead something more like 2 to the d, which, especially if you're allowing d to grow, just gets very bad very quickly. So there are some aspects in which Bohr sets are good, there are some aspects in which they are bad. And what that translates to in the way the proof finally looks is that a lot of the steps are a lot more technical and awkward to work with in the integers, for example, rather than an F3 to the n. In F3 to the n, we can work with genuine subgroups. In Z mod nz, we need to work with Bohr sets instead, which are much more approximate. And so the statements look a lot more technical. Again, which I've sort of hidden from this talk, but it is a problem that one has to deal with. Okay, so that's sort of one of the main characters of this approach are Bohr sets. I just want to introduce one of the other main characters of this story, which is the large spectrum. So sort of the key definition on this slide is the second display equation. So in general, if I have a subset A of my group, I can talk about the dual group, of course, the set of homomorphisms from G to the unit circle. This is the group of characters. And I define the Fourier transform of a set A in the usual way. So in particular, I just take the sum of, for a fixed character gamma, I take the sum of gamma of A over all little a inside A, and I normalize the sum by the size of the group. Okay, so this is basically an exponential sum over A. And in particular, when trying to understand the sort of the behavior of linear configurations or the additive behavior of A, the most important factors are going to be those characters where the Fourier transform is large. So those are really the central objects that I care about. And what is a trivial upper bound for the size of this Fourier transform? So if I choose the triangle inequality, I get a trivial upper bound of alpha, for example, right? So this absolute value of gamma of A is always 1. So the Fourier transform of A at gamma is always certainly going to be at most alpha in absolute value. So that leads me to define sort of make the following normalized definition. So the eta large spectrum of A, which we denote delta sub eta of A, is the set of all those characters gamma where the absolute value of the Fourier transform is at least eta times alpha. Okay, and you should just think of this as alpha is just the normalizing parameter. So eta ranges naturally between 0 and 1. And so it's just really capturing all those which are characters which are, in terms of absolute value, at least eta sort of percent large as they could be. And for future note, let me just point out there's a following easy fact about the large spectrum. So by Parseval's identity, if I sum up over the whole group the absolute value of the Fourier transform squared, and I change the order of summation and I use orthogonality, then it turns out that's just counting the number of solutions to the rather simple equation a minus b equals 0, again normalized by dividing by n, which is just equal to alpha. And then if you combine that with the definition of this large spectrum, then you get that the size of delta eta is at most eta to the minus 2, alpha to the minus 1. Okay, so it's quite easy to get an upper bound on the size of the spectrum by Parseval's identity. Okay, we'll refer to that upper bound later on. Okay, so I've now introduced a couple of the key players, and I just want to go back and remind you of the density increment overall strategy, which is that either we get many progressions or somehow we obtain a density increment. Now, of course, it's step 2 that's the hard part of this. Step 1 is usually sort of very immediate, and then most of the argument in these sort of arguments towards Roth's theorem is spent with showing that somehow you can deduce a strong density increment, and exactly how strong can you make it. So the bulk of our proof is in working out how to get a strong density increment from the assumption that are few 3APs in A. And so for the purpose of this talk, I've sort of summarized the plan in doing so as like a 5-step program. So I've given it these catchy slogans in all caps, just so when I refer to them later in the talk, hopefully it's a bit more memorable than just saying, oh, and as you recall, we then do step 3, because it's hard, and I think in the slide talk to quickly lose track of things like that. Okay, so the slogan form is size, non-smoothing, structure, boost, then increment. That's what we do. That's how we're going to obtain our final density increment. Okay, so let me explain what these steps actually mean. So if A has few 3-term progressions, then the first step is that we show that this implies that there is some eta and some associated spectrum, delta of eta, which has large size. And here I mean, by large size, I mean it has size roughly eta to the minus 3. Okay, so here eta can range from anything between 1 and alpha. And we really have no way of controlling where that happens, by the way. So it generally could be the case this happens eta very close to 1, in which case the size we get is quite small, but on the plus side, the size of the Fourier coefficients is very large. Or on the other hand, it could happen at eta very small, eta close to alpha, in which case, all right, the Fourier coefficients aren't very big anymore, but we have many of them. And in particular, note when eta is roughly alpha, then this lower bound of eta to the minus 3 actually agrees with this upper bound of eta to the minus 2, alpha to the minus 1. Okay. So when eta is roughly alpha, in fact, essentially what we're saying is that the size of the alpha level spectrum is as big as it can be, which is very unusual for a set. It's a lot of information. And it turns out actually the hardest case is when eta is roughly alpha. So all ranges of eta you do have to deal with somehow, but it turns out, at least for the methods that we use in our argument, the case that forces you to work the hardest is eta is roughly alpha. Okay, so that's the size step. What's next? So given this delta eta from the size step, we then want to somehow argue that it's additively structured in a certain way, which we call an additively non-smoothing set. So this terminology is from Bateman and Katz. I think, to my knowledge at least, they were the ones to introduce this concept to additive combinatorics. And this step and the following step were essentially the key parts of the Bateman and Katz proof. I'll explain what additively non-smoothing actually means in the next section of the talk. But just for now, it's some way of measuring some kind of additive structure of delta sub eta of A. We can't necessarily always guarantee that's true, but we can show that either it's true or we have a density increment of A, which is good enough anyway, and then we sort of exit and abandon the rest and carry on with our big density increment approach. Okay, so we have some set delta eta, which is large in size, it's additively non-smoothing, and then we want to apply some quite generic result about additively non-smoothing sets. So some sort of result which says that any additively non-smoothing set has a lot of internal structure. This step, in fact, is sort of in isolation. So you don't need to know that you're applying it to a set of spectra, which is a spectrum, for example. You don't need to know you're applying it on the dual group at all. It's just, in general, a statement along the lines of, if a set is additively non-smoothing, it has a certain type of structure, which again, I'll explain in the next section of the talk. Okay, so what's next is that we say we have the set delta eta, which is large, it has a lot of internal structure, and then we need an argument that allows us to boost this sort of initial spectral data from saying something along the lines of, we have a somewhat structured collection of somewhat large Fourier coefficients. We sort of want a bootstrap argument that allows us to deduce from that there exists a very structured collection of very large Fourier coefficients of A. And then finally, we conclude with a relatively standard step, which is a way of deducing an actual density increment from A from a structured collection of large Fourier coefficients. So those are the 5 main steps of our argument. So to put it into context about previous work, stages size and increments, so this was the first and the 5th stage, they're very sort of classical in some form or other, right? In a sense, they're present all the way going back to Roth. And certainly in the work of Bourgain and Sanders, these steps in the integers are very well developed, in particular how these steps actually work with Bohr sets, how one obtains a density increment via L2 method, for example, from a structured set of Fourier coefficients. So we use a lot of the same ideas and a lot of the work previously done by Bourgain and Sanders there. Stages non-smoothing and structure, so this was the 2nd and 3rd step. Basically in F3 to the n, that's exactly how the proof of Bateman and Katz goes. That's what allowed them to make their breakthrough, prove their breakthrough result. And so that was in F3 to the n. Adapting the 2nd stage, so non-smoothing stage, to the integers was essentially the approach that I took in 2014 to prove an n over log n bound. In fact, in a very rough sense, basically my 2014 proof, you can summarize as you just do 1, 2, and 5 here. So you skip out this sort of your very powerful 3 and 4 step. Okay, so sort of those parts were done previously. So what's new to our paper that really allowed us to push past n over log n? So first of all, although, as I said, the kind of ideas that go into this first size step, especially in the context of Bohr sets and the integers, have already been quite extensively worked out by Bourgain and Sanders, it actually turned out that to get into a strong enough form needed for the following steps of the argument, we needed even more information. So for example, we needed to know not just that there were many such characters, but also that there are many such characters that obeyed certain orthogonality properties with relation to spectra of Bohr sets, for example. And so we refined the first part of the argument into a sort of a more precise form that we need for our relative structural theorem. We improved the structure, the stage structure. In particular, we cannot use the result of Bateman and Katz as a sort of a black box. Okay, and this will make more sense in the next section, but basically they prove a result which is in terms of the actual additive energy. Because we're working with Bohr sets and everything is much more approximate rather than the rigid setting of f3 to the n, we cannot use their results about the additive energy and additively non-smoothing sets. Instead, we have to define all these things sort of relative to quite approximately subgroup objects. Again, this will make more sense in the following section. And finally, step 4, the boost stage, is certainly in its current form new to this paper. So one needs some kind of suitable spectral boosting method. In a sense, the previous, the work of Bateman and Katz had an alternative approach, as did the recent work of Schoen, in how one deduces from this stage 3 structure in getting a sort of a good structured piece. But really, to get past this barrier of n over log n, you really need to, so when I said very additively structured and very large Fourier coefficients, you really need to jump up quite a lot. So you need quite a powerful boosting method from jumping from somewhat structured and somewhat large to very structured and very large. So we had to come up with a new technique for doing that. So those are, I guess, is the punchline. For those of you wondering what's new to this paper, I would say it's probably roughly can be separated into those 3 categories. I think that's my final slide yet for the first part of the talk. I'm not going to say anything more in the rest of the talk about the first step, mainly because to even say precisely what the new bits are, you have to write down these very long technical statements involving Bohr sets, which would sort of take half an hour to even state and wouldn't be particularly illuminating. But for those who are interested, you can go and consult the paper. But I really wanted, I guess, to give a very high-level overview of what the kind of structural results I mean in part 2, and also what kind of spectral boosting method that we use is. I think those are the sort of the 2 really interesting new parts of the proof. So as I say, I'll break now, I guess, for like 5 minutes or something, and allow for if there's any sort of quick questions in the break, and also to allow people to have a breather, and then in the rest of the talk I'll go into a bit more detail about this additive non-smoothing and spectral boosting.
Thanks, Tom. So should we resume at 58 minutes past the hour? Does that work?
Okay. Yeah. Sean?
Great, yeah.
And then obviously further questions are welcome at the end. Okay. So now let me talk about additively non-smoothing. And for this part of the talk, you can now completely forget it about the Fourier transform, about 3-term progressions, about density increment, about everything, and it's sort of a purely additive combinatorial type of question now. Okay, so the notion of additive energy is ubiquitous in additive combinatorics, and in particular, it's a very convenient sort of smooth analytic way of saying that a set delta is additively structured somehow. So its definition is that it just counts the number of quadruples, gamma 1, gamma 2, gamma 1 primed, gamma 2 primed inside delta, which lie inside an additive quadruple, right? So gamma 1 plus gamma 2 equals gamma 1 prime plus gamma 2 primed. So note the trivial bounds that obviously E4 of delta is always at least delta squared because of the trivial solutions, and is always trivially at most size of delta cubed, right? Because if I fix any 3, then the 4th one's also fixed. So this means that it's good to consider a normalized version of this additive energy. So we use the letter tau for this. So by definition, E4 of delta is equal to tau times delta cubed, which means that tau lies inside the range delta to the -1. Tau is at least delta to the -1 and is at most 1. And in a sense, obviously, the larger tau is, so the larger the energy is, that corresponds to a set delta having more structure, right? So there are more solutions to this equation. Delta is more structured, the larger tau gets. And we also want to consider the higher additive energy, E8, which it counts a very similar thing, just that we now allow more variables in this equation. So it now counts sort of the 8 tuples, gamma 1 up to gamma 4 primed, such that the sum of the first 4 equals the sum of the second 4. Obviously, you can generalize this for any sort of E to M of delta, which indeed we do require in the paper. But for the purpose of this talk and this simplified sketch, I'm just going to talk about E4 and E8. So it's quite straightforward using the Cauchy-Schwarz inequality twice to prove that actually you get a lower bound for E8 in terms of E4. So in particular, one can prove that E8 of delta is at least tau cubed times delta to the 7. So note as well, I get similar trivial bounds for E8. So E8 is at least delta to the 4 and is at most delta to the 7. Okay. So sort of the natural normalized quantity is E8 of delta divided by delta to the 7. Okay. So in particular, this sort of normalized E8 energy is at least the cube of the normalized E4 energy. Okay. So that just holds for any set delta, whatever tau is. And we say that a set is additively non-smoothing if this is almost tight. Okay. In other words, E of delta is approximately tau cubed times delta to the 7. So E8 of delta is almost as small as it could be, given whatever size E4 of delta is. So this concept, this terminology comes from the paper of Bateman and Katz. And again, to the best of my knowledge, they were the first to really notice that this was a useful property, and indeed that one could actually use this property to prove these quite strong structural theorems that I'll talk about in a minute. It's very important to stress, I guess, that we are not assuming anything at all about the size of tau relative to delta. Okay, so in particular, we're not assuming that tau is close to being 1. Indeed, note that if tau is close to being 1, then somehow such a set is trivially non-smoothing, right? Because if tau is roughly 1, then tau cubed is also roughly 1, and E8 of delta can't be much bigger than delta to the 7. So again, I'm being sort of vague in my quantitative parameters here. But yeah, so this definition makes sense whatever the size of tau is, which is in contrast to most of additive combinatorics, which really focuses on the regime where tau is basically constant, okay, where the energy is almost basically delta cubed, which corresponds, for example, to the regime where the doubling constant is constant as well. So this is sort of the range of applicability of things like Feynman's theorem, for example, or Alexander Gauss and things like that. Quite classical tools of additive combinatorics. Obviously, they do allow some kind of dependence of tau on the size of delta, but usually, I mean, they sort of lose steam once you get past, say, logarithmic in delta. And it's very important that we're not putting such restrictions on tau in this work, because it turns out for the sort of delta we're considering, namely the sort of large spectrum, so delta is secretly delta eta of A, it turns out we actually expect tau to be the size of delta to the minus 2/3. Okay. So I won't go into why, but you know, sort of the calculation you can do, it turns out that's roughly the size of tau you expect. In particular, this is polynomially small in delta. So the sort of the traditional tools of additive combinatorics, like Feynman's theorem, just won't tell you anything at all useful, just from this sort of energy information. Okay. So this is the definition of additive non-smoothing. So E8 of delta is roughly tau cubed times delta to the 7. So I'm going to demonstrate this by a couple of examples. And first of all, obviously, even more important, a non-example, because you might be asking, well, is every set additively non-smoothing? So the answer is no. And in particular, a random set is not additively non-smoothing. So this is really good, obviously, because if we hope to prove a structural result about additively non-smoothing sets, I certainly shouldn't be claiming that I'm proving a structural result about random sets. And that should set up alarm bells. So it's good that random sets are not additively non-smoothing. So it's quite easy, it's a quite straightforward calculation to do, sort of exercise in probability, that if I choose a random set of delta of density little delta, then one can work out that E4 of delta is, the normalized energy is roughly little delta, and the normalized E8 energy is also roughly little delta. Okay, which means that E8 is actually much larger than this lower bound of tau cubed, right? So E8 is roughly, the normalized E8 is roughly tau, instead of being tau cubed. So instead, we say that a random set is additively smoothing. And sort of the motivation behind the terminology, by the way, comes from the idea that I expect A plus A to be more structured than A. I expect A plus A plus A plus A to be more structured than A plus A, and so on. Right? As I add the set A to itself more times, just like convolving a function with itself more times in analysis, I expect this sort of function to smooth out. I expect the additive behavior of the set to smooth out. If E8 of delta is very large, then that means that sort of the fourfold sum set is behaving particularly structured. If it's a lot larger than I expect from knowing what E4 of delta is, that means that the fourfold sum set has become somehow a lot more structured than A plus A, than the twofold sum set A plus A is. Okay, so it's additively smoothing if E8 is bigger because I've smoothed out the set a lot more than I might naively expect by repeated addition. And additively non-smoothing says that that doesn't happen. So essentially all the structure of delta is already present in the first stage. I don't gain anything by repeated addition. Okay, so that's a non-example of additively non-smoothing set. What's an example? In fact, there are two quite different examples one can give. So the first, and again, I'm going to be very informal and sort of use approximately equal signs here. One can work out precise form of these examples according to taste. So the first example is where it's basically of the form H plus D, where H is somehow a structured set, and D is any set. It could be a random set, it could be a dissociated set, or anything like that. By structured set here, you can sort of pick your favorite notion of structure. So you can pick H to be a set of very large additive energy, for example, or small doubling constant, or even just H to be a genuine subgroup, if those are available. But importantly, H and D should be somehow orthogonal, right? So in particular, like the size of this set, H plus D, should be the size of H times the size of D. And if I sort of shift translate by things in H, that shouldn't really interact much with translates by things in D. Okay, so if I pick a structured H, some sort of random set D, which are orthogonal in this way, and I consider their sum set, then it turns out that this is indeed additively non-smoothing. Okay, so here the correct choices of size are the size of H should be tau times the size of delta, where tau is again whatever size, whatever sort of tau I'm trying to achieve. So tau could be anything between delta to the -1 and 1. And D has size tau to the -1, okay, which it has to make this work out, right? So the size of the left-hand side is the same as the size of the right-hand side. Okay, so I won't do the calculation here. I encourage you to try it. It's a fun and instructive calculation, sort of heuristic calculation to work out what the E4 energy of this is, what the E8 energy of this is. And it turns out that indeed the E4 is basically tau times delta cubed, and the E8 is basically tau cubed times delta to the 7. The second example is instead I take a collection of different structured sets, say HI. Now these could be completely different, right? So for example, if you're thinking of them as being subgroups, they can be completely different subgroups scattered all over my ambient group. They don't need to have any particular relation to each other, other than they are basically orthogonal again. So like translates by things in HI shouldn't really affect translates by things in HJ in general. So if I take, and let's say they all have roughly the same size. So if I take such HIs and take the disjoint union of tau to the -1/2 of them, then again, one can do the calculation, sort of this heuristic calculation, and it turns out that this set is also additively non-smoothing. Okay, and again, obviously to make the size work out, each HI has individually sized roughly tau to the 1/2 times the size of delta. So that overall this ensemble has size the size of delta. Okay, so there are two examples, and note that they really are quite different to each other. So in the first one, you can think of, for example, as I have the disjoint union of tau to the -1 structured sets, which are all cosets of the same subgroup, for example. Okay, so they're individually smaller, so there's more of them, but they have quite a lot in common with them, namely they're all sum translates of the same underlying subgroup. Whereas in the second one, I have fewer of them, they're individually bigger, but now I'm not assuming they're certainly not translate to the same subgroup. In fact, they're sort of the opposite. They really are very sort of scattered big pieces all over my ambient group. Okay. So unlike, for example, when you're trying to prove structural results like the Freiman root inverse theorem, there's essentially only one sensible type of example of a set with small doubling constant, which is something like an arithmetic progression or a coset progression in general. It turns out for when you're trying to prove a sort of a structural result for additively non-smoothing sets, there really are sort of two genuinely distinct examples, and one can interpolate these in fairly natural ways as well. So there's a whole family of genuinely different examples. Okay. But it's still possible to prove some kind of inverse result because they have something in common. Namely, there exists some x inside delta and a structured set H inside delta, such that the additive energy between X and H, right? So this is defined in the obvious way. So it's counting the number of pairs X1 and X2 and H1 and H2, which lie inside this additive quadruple relation, is almost maximal. So in other words, that's at least h squared times the size of x times some tiny constant. And also, I can say something about the size of these, not individually, but taken together, I can say that the product of their size is roughly tau times delta squared. Okay, so this is true in both the previous examples. So for example, when delta is roughly h plus d, I can take x to be the whole set delta and h to be precisely the structured set h. And when delta is this disjoint union of subgroups example, I can take x to be the same as h, just to be one of these fixed pieces for any of the fixed pieces. Okay, so they have this thing in common. And it's exactly that kind of inverse result, which was proved by Bateman and Katz. So if a set delta is additively non-smoothing, in other words, if E4 delta is roughly tau delta cubed, E8 is roughly tau cubed times delta to the 7, and again, I want to stress tau could be anything, basically. It could be anything from 1 down to delta to the -1. Then there are x and h inside delta, such that the energy between x and h is basically maximal up to constants, and the product of their size is tau times delta squared. Again, this is sort of only an informal statement, so I'm not going to try and describe the quantitative dependence in the conclusion here. And also note that in the previous slide, I pointed out that this set H is in fact structured. That's not in the conclusion here, but one can quite easily derive it from the fact that E of xh is almost maximal. Basically, at this point, you work out exactly what kind of structure you need, and then you sort of bring in whatever tool from additive combinatorics you require. So, for example, in Bateman and Katz's paper, they used the asymmetric Biot-Zimmer Gauss here to basically somehow transform H into having a small doubling constant. In our paper, we don't need to do that. Instead, we use a dimension. We sort of say that instead that H is contained inside the large symmetry set at X, and then use a result inspired by a bound of Shkredov and Yekanin to say that therefore the dimension of H is bounded. But sort of it's more like, you can combine that with other results to taste depending on what you require of it. Okay, so as I mentioned before, it's still morally this kind of result that we use, but unfortunately we can't use the theorem of Bateman and Katz as a black box. Essentially because we're doing all this stuff relative not to subgroups, but relative to Bohr sets, which are only approximately structured. And in particular, we can't really obtain any useful information about the actual energies E4 of delta or E8 of delta. Right? There's just no way to get any sort of sensible, useful bound on these quantities, so we can't hope to achieve these hypotheses. And instead, the natural thing to work with is relative energy. So this is a very similar definition. So again, I'm counting the number of quadruples, but now I sort of tweak what I mean by equality, basically. So instead of saying gamma 1 plus gamma 2 equals gamma 3 plus gamma 4, I want to say that gamma 2 plus gamma 2 equals gamma 3 plus gamma 4 up to some translate by something inside this sort of this object gamma. And here gamma is itself some approximately structured set. And sort of morally what we're doing is, I guess, we're quotienting out by gamma, for example. So in particular, for example, if gamma is just the singleton 0, then this is exactly the previous notion of additive energy. If gamma is a genuine subgroup, then you can literally pass to the quotient group and look at the projection of delta inside that quotient group, and then work with that. So again, if you really are working with genuine subgroups, then you basically can directly apply this theorem of Bateman and Katz. But when gamma is not a natural subgroup, it's only an approximate subgroup, you sort of need to prove a new result directly, which is what we do. So the main thing to focus on here is that the hypotheses and the conclusion are essentially the same, except that all the energies are now relative to some gamma. Okay, so I'm assuming now a statement of control on E4 of delta relative to gamma and E8 of delta relative to gamma. And again, it's the same sort of relationship between them, this additively non-smoothing relationship. And I get the same conclusion, there's x and h inside delta, so that the energy between x and h relative to gamma is almost maximal. And again, they have this, the product of the size is restricted. Now, of course, I can't hope to prove that for completely arbitrary sets gamma. I need to assume that gamma is something like a subgroup, at least approximately. So there are certain structural assumptions that go into this. And also I need to assume that delta is sort of basically orthogonal to gamma, which again makes sense if you think about what happens if gamma is a genuine subgroup. That roughly that corresponds to sort of choosing a co-state representative for delta inside the quotient group to say something about the E4 of that projection. And again, so the actual technical assumptions that we need are fairly lengthy to state. And in fact, it turns out we don't actually work with a single gamma. And in fact, we get an ensemble of gamma i's, which we call an additive framework. And in our application, the gamma i's turn out to be spectra of Bohr sets. Sorry, to these sort of these are the approximate subgroup objects we work with. And we need to sort of work with a whole ensemble of them rather than just fixing one, because the proof of this is sort of an iterative argument where we jump back and forth between different scales quite often. And we need there to be sort of basically different scales available so we can sort of always exit to a favorable one. I won't really say anything about the proof of this, just to stress that it is entirely elementary. It's long, and I think it's probably the most difficult part of the whole paper. So it takes about 20, 25 pages altogether, maybe. But it is elementary in that it uses just the Cauchy-Schwarz inequality and the pigeonhole principle, and never uses the Fourier transform or anything like that. Also, I mean, one could write down our proof in the simpler non-relative case, so there aren't any of these gammas floating around, and then it would basically be a new proof of the original result of Bateman and Katz. The language would be quite different, but there would be many similarities in what Bateman and Katz do, and certainly our proof was heavily inspired by a lot of the sort of pigeonholing and elementary methods that Bateman and Katz used. Okay. So now I'm going to move on to talking about this other key component of spectral boosting. So essentially the situation where it's used is this. So after a lot of technical maneuvering and applying some sort of structural result like on additively non-smoothing sets, as mentioned in the previous slide, essentially the hardest case you finally get into a situation that's like the following. I have some delta, which is the alpha level spectrum of A, which is of near maximal size, roughly alpha to the -3. Again, remember that's the biggest that delta alpha can be. And I know that it contains some H, which is very structured. So you can think of it, for example, as being approximately a subgroup of size alpha to the -1. Now, since H is a subset of delta, then we certainly know that by definition, if I have a character inside H, then the absolute value of the Fourier transform at gamma is at least alpha squared. Okay. So that's naively all I can really say. So that gives me a very structured ensemble of Fourier coefficients which are somewhat moderate in size, right? So H is very structured. It's basically a subgroup. It's of size roughly alpha to the -1, and everybody in it has basically Fourier coefficient around alpha squared in size. Alternative approaches at this point, for example, this is roughly what Bateman and Katz do, are to basically increase the size of H so that one can get a better density increment from that. But you do that at the expense of losing some of this very strong structure, right? So sort of it roughly corresponds to something like in this sort of H plus D, I sort of have located this H inside my spectrum, and then I'm maybe going to sort of select some very special translates from D and sort of throw those in as well. So I'm blowing up the size of my set. I lose this sort of very strong subgroup-like property, but on the other hand, I get many more characters. As I mentioned before, that approach doesn't really work for the integers just because it's really not strong enough. You really need to be able to maintain this really strong amount of additive structure that one obtains from the structural theorem, basically saying that H is like a subgroup. Okay, so instead we use spectral boosting. And again, it's the techniques involved are purely elementary. So it's Cauchy-Schwarz inequality, pairwise identity, and a little bit of pigeonholing that basically allow us to boost the spectral information. So again, naively, if something's in H, then we know that the size of the Fourier coefficient is alpha squared. And instead, basically, we can say that if something is in H, then on average, the Fourier coefficient is actually larger than we expect. It's actually alpha to the 3/2. This saving of alpha to the 1/2 is really crucial it's completely necessary to get this to work in the integers at all. And it's basically the idea is that we started out with a spectrum at level alpha, we found some additively structured piece, and then we use the additive structure of the piece to be able to sort of boost up the spectral level that that piece lives in. And in particular, that allows us, because we continue to work with H throughout, so it remains really very structured, and now the size of it hasn't changed, the structure of it hasn't changed, but the spectral level at which it morally lives is much higher. So that gets us a much better density increment from it. Again, our method is sort of use the Cauchy-Schwarz inequality and parcel-wise identity. It doesn't actually always work. We don't have really a clear counterexample that shows that it can't always work in the situation that we want. But fortunately, it turns out not to matter, because if our method fails, then we can actually deduce very strong physical information about the set A itself. So at that point, you can sort of forget about spectra, forget about the structure, forget about everything else. And you actually have a lot of physical information about A itself. In particular, the LP norm of the convolution of A with itself is going to be large for large P, which is ideal for an application of almost periodicity. Okay. So indeed, this is basically the approach that Olof Sisask and I took in last year's paper, where we just sort of said it's dichotomy, that either the LP norm of the convolution is large or the LP norm of the convolution is small. So in this case, basically we apply what we did in the LP norm of the convolution being large case, and then we get a strong density increment using physical methods. Okay, and that's what I'll say about spectral boosting. Again, there is quite a short instructive calculation that one can do to give you a flavor about what's going on, which is in section 3 of the paper. So I encourage you to look there if you want a demonstration about how this method actually works. Okay.
Tom, can I ask, is this saving of alpha to the 1/2, would any power of alpha be okay here, or?
So certainly not any power of alpha. I think you could probably get away with a saving of, say, alpha to the 1/4. Yeah, so like, for example, if you've got a lower bound of alpha to the, what's between 3/2 and 2? 7/8, no, 7/4. Then that would be enough, for example, to get the kind of final result that we did. But it turns out, in fact, which is, I think, a nice feature of the approach, it very naturally gives you alpha to the 3/2. And I'm just about to talk about, in fact, that's a really strong saving, because it means that basically if spectral boosting was the only part we had to worry about, we would already get bare n-type bounds. We'd already approved this conjecture. So somehow that says, at least to me, that this spectral boosting is, or this part of the argument is already somehow the right thing to be doing. This part is sharp, because this sort of very nice elementary argument naturally gives you a really strong density increment. So actually, so I'll go on to the next slide. Just to remind you of this conjecture that I brought up earlier. And so although this conjecture, just if you look at the upper bound of this conjecture and the upper bound of the theorem that we prove, they seem very far apart from each other. And one might reasonably wonder, okay, so what should we expect the next progress to be? Should we expect, the value of C to be improved a little bit, and then maybe n over log n squared, and maybe n over log n cubed, and so on and so on. So I really don't think that's what will happen. I really expect sort of the next substantial step to be possibly even proving something like this conjecture. I think a lot of the techniques sort of introduced by Bateman and Katz and developed further in our paper already morally give you density increments which are strong enough to prove exactly this result. So I think there's only one really notably bad part of our argument, which is in the non-smoothing step of that argument. So that was the step where we said, okay, I have this set delta eta, this large spectrum, and I know it's large, and now I want to deduce somehow that it's additively non-smoothing, right? I need to do this to fit with my whole Bateman-Katz style approach, because I need to apply this structural result with non-smoothing sets to be able to then apply spectral boosting and so The trouble is the way we do that is actually relatively crude compared to the structural result for non-smoothing sets and the spectral boosting methods. The way we do that essentially is basically suppose that delta is not additively non-smoothing, so the E8 is a little bit bigger than we need. Then you sort of apply Holder's inequality to just boost that up to saying that some really higher additive energy E2m, say, is larger than you expect. And then you can use that with sort of a random sampling argument to say that therefore we can find some sort of reasonable subset of delta with reasonable amount of additive structure. And then we exit with that. Now, fortunately, that's enough to get this pushed past the log barrier, but it's really not the kind of spectral boosting level of information where we got a very structured set of coefficients which are very large. In that case, we're sort of forced to exit with a reasonably structured set of coefficients which are quite large. So that's really the weakest, I think, part of our argument. And certainly, so I believe, for example, that the something like the structural theorem qualitatively certainly can't be improved, certainly room for quantitative improvement there. I believe something like spectral boosting, again, qualitatively is reasonably sharp. But certainly, if you just look at the methods that we use, it's sort of obviously the wrong thing. It's sort of obviously a fairly crude sort of patch in a way that fortunately is strong enough to allow us to carry over and apply these powerful methods that come later. But it definitely doesn't feel like the right thing. And so I think it's fair to say that we believe that an improvement to that part of the argument, we don't have any sort of very clean, you know, if you prove exactly this conjecture, then you prove this upper bound for R of n, partially because there are ball sets everywhere, even writing down a technical, precise version of the conjecture would be difficult. But certainly we believe that any substantial ideas in that direction, combined with the structural result in spectral boosting, this paper, should yield further progress in R of n. And in particular, I would hope that something along the lines of this upper bound here, which is approaching bare in strength. And I haven't written in the talk, but at the end of our paper in the final section, we sort of did write down a couple of relatively sort of precise-ish conjectures, which sort of attempt to highlight the gaps in our knowledge about what the structure in these spectra can look like. So if anyone's interested, I encourage you to just sort of go ahead, skip to the last page of the paper and just look at those conjectures. And even, for example, in F2 to the n, they are, as far as I know, open conjectures. And I think any ideas, even in F2 to the n, for example, would be immensely useful. So you don't even have to worry about ball sets if you don't want to. Okay, and I think I'll stop there for questions. Thank you.